Greetings! Isang pagbati na puno ng kaalaman. Our lecture for today will be on beam deflections. However, we will be dealing with statically indeterminate members. This lecture will focus on double integration method still. This is lecture number 21. Now, when we are dealing with statically indeterminate beams, how do we know that a member is statically indeterminate? Take, for example, this propped cantilever beam. It's fixed at A and supported by a roller at B. Our first step, as always, is to draw the free body diagram of the beam. If I draw the free body diagram of the beam, I should know that if I have a fixed support, there are force reactions along X and Y, and of course, a moment reaction. And if I have a roller here at B, the only reaction here is a vertical support reaction. Now, I have four unknowns, given that there are four support reactions in this beam, but I only have three equilibrium equations: summation of forces along X and Y and summation of moments. Since my number of unknowns is greater than the number of available equilibrium equations, we can say that the beam is statically indeterminate. Therefore, I need to use compatibility equations in order to solve the problem. Now, your question might be, what are the compatibility equations needed? The compatibility equations will actually come from your boundary conditions. So from your boundary conditions, these are actually additional equations in order for us to solve the support reactions. Now, again, please remember that the additional support reactions in the beam which are not needed to keep it stable are what we call your redundant supports. Meaning, in a propped cantilever beam, in our previous example, as we have shown, it is okay that the beam is actually cantilevered. There's no need for the roller. So that's the moment reaction is actually a redundant reaction. And the number of redundants is defined as the degree of static indeterminacy. Or what you can do to determine this is count the number of unknowns. In our previous example, it's 4. And count the number of available equilibrium equations, which is 3. Subtract 4 and 3, you get 1. So the problem in the previous figure is actually indeterminate to the first degree. How do we solve statically indeterminate beams? So first step is to select our primary structure. When we say primary structure, from the original figure as shown here, what I do is make the member stable. Since we know that there are redundant supports, what I can do is take out from the primary structure something that is stable. So I can say I can take out a cantilevered beam, or I can take out a simply supported beam. But then again, remember that these two primary structures are still not the same as the original figure. Therefore, what I will do is I will replace the redundant reaction with an equivalent force or a moment, meaning from this first figure over here, primary structure, to go back to the original figure, I need a force reaction. That's the redundant. Similarly, for this second figure, for this simply supported beam to be the same as this original figure, there's actually a missing moment reaction. So these red arrows over here are what we call your redundant forces or redundant support reactions. After which, I now need to apply my compatibility equations, which are actually boundary conditions. Remember, I am applying boundary conditions at the original figure over here. Therefore, I can say that since this is a fixed support, I can say that the slope at the fixed support is 0. I can also say that the displacement at the fixed support is 0. And I can say that I have a roller here, that the displacement at the roller is equal to 0. Here it is written as free end because right, the roller reaction is actually a redundant reaction. So that's still okay. Similarly, for this second figure, we still have the same set of boundary conditions because, again, I am applying the boundary conditions to my original figure over here. Okay? Let's try to look at this example. For the prop cantilever beam with loading as shown, determine using the double integration method all the support reactions and the deflection at point B. Okay? So at this point, kindly make sure that you grab a copy of the figure while I set up. Okay? So please get a snapshot of the figure. Okay? Please get a snapshot of the figure while I try to change and get my solver. Okay, now, okay, this is the problem. Our first step always is to use equilibrium and draw the free body diagram and determine the support reactions. However, what is special when we are dealing with indeterminate beams is that you should not be able to solve for the support reactions. In step 0, what you can only obtain are actually relationships between the forces. Okay? You should not be able to get any numeric answer, only relationships. Okay? So to draw the free body diagram, please remember that this is a fixed support, so I have a force reaction at A. Okay? I also have a roller reaction at C, a support reaction at C, and I have a moment reaction M sub A over here. Now again, I just assumed that the reaction is clockwise. You can always assume any direction. After which, I can now apply my equilibrium equation. My first equilibrium equation is summation of forces along the y direction. Okay? This is equation number 1. Again, please remember that you won't get any numerical answers yet, only relationships. Also note that I don't have any force along the horizontal since I don't have any horizontal force in the problem. After that, I can use another equilibrium equation. I can use a moment equation. I'll sum moments about point A, taking counterclockwise as positive. Okay? The red text here shows the lever arm for each force. So this is equation number 1 and equation number 2. So again, after step 0, what you should only obtain are relationships between the forces and the support reactions. No numerical answers at all. Okay. Step 1, establish the coordinate system. As you may see, the step-by-step procedure is actually the same as what we have been doing in the previous in our previous problems, in our previous lessons. The only difference is that in step 0, you won't be able to get support reactions, numerical answers for your support reactions. Okay? So again, for us to not have any difficulty, step 1, I'll set my origin, right, as point A. Okay? So my origin is at A. Okay? So the leftmost part. Then my positive is to the right. So if my positive is to the right, okay, what is considered as the end of the beam? The end of the beam is C. Okay? So it's the rightmost part of, okay, the rightmost part of the beam. Now, my next task is to write the moment function. Okay? So take note that in double integration method, the force at the rightmost, or at the end rather, is not included in the moment function. Therefore, if I look at this, okay, the reaction R sub C should not be included since it is found at the end, okay, at the end of the beam. Similarly, okay, I have a distributed load which is not loaded up to the end. Therefore, I need to perform dagdag bawas. Okay? So what I'll do is, upon performing dagdag bawas, okay, I'll add a uniformly distributed load up to the end. However, whatever I added, I also need to remove. Okay? So I should have the same magnitude but opposite direction. Oops. Okay? Which is also 14 kilonewtons per meter. Okay? Now I can write my moment function. So my moment function, given this figure over here, would be d squared y over dx squared is equal to 1 over ei. Then, please take note that the moment reaction, I assumed it to be clockwise. So in our previous discussions, that's positive. So ma, x minus 0, it starts at x equals 0 since this is our origin, okay, and taking to the right as positive, raised to 0, plus r sub a, the reaction, x minus 0 raised to 1, minus, since I have a uniformly distributed load that's downward, that's minus omega over 2, so 14 over 2, x minus 0 raised to 2, plus, okay, this distributed load that we need to remove, so 14 over 2, x minus 0, and it's starting at it starts at x equals 5. Okay, so that's x minus 5 raised to 2. Okay, so this is now our moment function. Again, this should be 5 because the uniformly distributed load, okay, which is upward, started at x equal to 5. Okay? After which, I now need to perform my double integration. Okay? So to perform my double integration, okay, let me call that equation A. This is now the slope. Okay? Then, I integrate again one more time. Okay? Please do not forget the constants of integration, C1 and C2. Okay? This is now the deflection. Okay? After that, step number 4 is to apply my boundary conditions in order to solve for C1 and C2. Also remember that my boundary conditions are actually my compatibility equations. And if the value inside the bracket, as a reminder, is negative, the value becomes 0. Okay, so going back to my original figure, I should know that I have a fixed support over here. Therefore, my first boundary condition would be, I can say that dy over dx is equal to 0 at x equals 0. So that's my first boundary condition. Therefore, I can actually use equation A. So using equation A, okay, I'll just copy equation A. Okay? So this is my equation A and equate it to 0. Okay? But what I'll do is, I'll substitute the value of 0 for x. So I'll just write 0 for all values of x. So in this case, 0, 0. I just copied equation A, 0, and 0. Now, if you'll try to notice, 0 minus 0, that's 0. 0 minus 0, that's 0. Still 0. And I have here 0 minus 5, that's negative, so that's 0. Okay? Therefore, that tells me that C1 is equal to 0. Okay? Let's continue. What's our second boundary condition? I have a fixed support over here. So aside from the slope being equal to 0, okay, the deflection is also equal to 0. Therefore, I can say that y equals 0 at x equals 0. Therefore, using equation B, okay, so using equation B, I'll just copy equation B and equate it to 0. However, I'll substitute 0 as the value of x in equation B. Okay? Again, I'm using equation B because that's deflection. Okay? So I'll change 0, the x to 0, okay? All x's to 0. Okay? Therefore, once I evaluate 0 minus 0, that's 0. 0 minus 0, 0. 0 minus 0, that's still 0. 0 minus 5, that's negative, so that's still 0. Right? Therefore, that tells me that C2 is equal to 0. Okay? However, going back to my problem over here, I actually have 3 boundary conditions. I haven't considered, right, the boundary condition imposed by the roller, right, at end C. Therefore, I can say that another boundary condition is that y is equal to 0 at x equal to 8. Okay? Therefore, since that's a deflection, I'll still use equation B. Okay? So I'll just copy equation B over here. Okay? However, what I'll do is I'll just substitute the value of 8 to the variable x in equation B and equate everything to 0. Therefore, this is just 8. Okay? This is 8, 8, 8, 8. Okay? And I know that 0 times 8, that's just equivalent to 0. C2 is 0. I'll cancel that out. All the other terms actually have positive values inside the bracket. Therefore, I need to evaluate, okay, such that I can say that I now have, okay, 0 is equal to MA over 2 times 8 squared plus RA over 6 times 8 cubed minus 7 over 12, 8 to the 4th, plus 7 over 12. 8 minus 5 is 3 raised to 4. This is now called equation number 3. Okay? Since I cannot solve this equation because I actually have 2 unknowns in that equation, M sub A and R sub A. Now, as you can see, I actually have 3 equations now. So what I can do is, I can go back and solve equations 1, 2, and 3 simultaneously. Remember that equations 1 and 2 are actually your equilibrium equations. And equation 3 is your compatibility equation coming from your boundary condition. Once I have solved equations 1, 2, and 3 simultaneously, you will see that R sub A, this is just the time when you can solve or you are going to solve, you can solve the support reactions numerically. Therefore, R sub A is 58.464 kilonewtons upward. R sub C is 11.536 kilonewtons upward. And M sub A is negative, meaning our initial assumption is wrong, right? Such that M sub A should be 82.712 kilonewton meters in the opposite direction, which is counterclockwise. Okay? So that solves our first question. Okay? What are the support reactions? Okay? Now that I know my support reactions, I can proceed to the second question, which is, what is the deflection at point B? Okay? So going back to our figure, okay? So what is the deflection at point B here? Okay? So what I can do is, again, I'll just use equation B. Okay? So my equation B, from equation B, I'll just copy equation B. Okay? So this is my equation B. I can now solve the deflection, okay, at B, using equation B. By knowing that, or by saying that, I am being asked, what is Y, okay, at X equal to 5. So Yx equals 5 because if I go back to the figure, right, point B is actually found at a distance x equal to 5. Therefore, in my equation B, what I will do is I'll just substitute, I'll copy everything, but I'll substitute the value of 5 to the variable x. Okay? Therefore, copying equation B, also I already know the support reactions. I know that MA is negative 82.712. because my initial assumption is wrong. Okay? So that's negative 82.712. Okay? Similarly, I know that RA here, okay, is already 58.464. Okay? Therefore, I can now substitute everything. Then, similarly, I can use the value of 5 for x. So I'll just substitute and copy from equation B. X equals 5, x equals 5, x equals 5. Okay? Well, for C1 and C2, I already canceled that out since C1 and C2 are both equal to 0. Okay? From this one, okay, since all the values in my bracket are positive, I can now evaluate, okay, and say that once I evaluate, this is actually equal, kindly confirm, negative 180.486 all over EI. Okay? Our unit of measurement, since this is deflection, force times unit length. Okay? And to convert everything to newtons and millimeters, this is negative 180.486 times 1,000 raised to 4 for this to be Newton millimeters cubed. And recall from the problem that E is 200,000 megapascals, okay? And I is 216 times 10 to the 6 millimeters to the 4th. Such that my final answer here is negative 4.18 millimeters. But since I got a positive answer, that's 4.18 millimeters downward. This is now the deflection at point P. Okay? Are there any questions? I hope you were able to understand. Okay? Before we proceed to the next example, kindly absorb the problem and double check if my answers are correct. Okay? If my numerical computations are correct. Okay? Now, let's try to go back to our next example. Okay? Example 21.2, right, is actually a statically indeterminate problem. However, you are being asked to solve it using the area moment method. Right? But this video lecture will concentrate on the double integration method first, so you can try and solve this at home. Next problem is practice problem A. We have here a prop cantilevered beam, and using DIM, we're being asked to solve, right, the support reactions at A and B. However, right, we have here the flexural rigidity already, which is 200,000 kilonewton meter squared. Right? So at this point, kindly get a copy of the figure. Kindly get a snapshot of the figure as I transition to my solving board. Okay? Now, please do remember that our steps that we have, that we are actually doing here are the same. However, we are only imposing additional conditions, boundary conditions, in order for us to solve our support reactions first. Okay? So our steps will not change. Look at this. Using equilibrium to relate the forces, right, to each other and to the support reactions. Again, step 0, you should not be able to solve the support reactions numerically. You should only be able to relate them to each other. Okay? That should be clear. Now, I have a prop cantilevered beam. Therefore, I have a roller reaction at B. I have a vertical support reaction at A and a moment reaction at A, which I just assumed the direction. Next step is to use equilibrium, okay, in order to relate the forces to each other. So I will have equation 1 as the summation of forces along Y, and I'll use summation of moments about point A as equation number 2. Again, if I look at equations 1 and 2 over here, what I was able to accomplish is to relate the forces to each other and to the support reactions. But please take note that I should not have any numerical answers at this point. Step 1 is to establish the coordinate system. since my origin, where x equals 0, I'll just set at A. Okay, so this is my x equal to 0. And for us to have a conventional problem solving, okay, and we won't have any difficulty, I'll just say that my positive direction is to the right. And if my positive direction is to the right, what is the end again? Okay, the end is C, or the rightmost part of the beam. Next is I need to perform, okay, or write rather, my moment function. But then again, number one, there is no force found at the end. Therefore, there is no force that should be excluded in the moment function. Okay? Similarly, okay, do I need to perform dagdag bawas? There is no need to perform dagdag bawas. Okay? There's no need to perform dagdag bawas because my distributed load is already loaded up to the end of the beam. Is that clear? Therefore, I can now write my moment function. My moment function is simply d squared y over dx squared is equal to 1 over ei. Okay? Let's start with the moment function, which is, I assume, clockwise. So in my moment function, from our previous lectures, that's positive m sub a x minus 0 raised to 0 plus r sub a x minus 0 still because it started at x equals 0 raised to 1, right? Plus r sub b, right, which is upward, I assumed upward, x minus a, which is 6 because the support reaction b is found at x equals 6 raised to 1, minus, right? Why is it minus? How about the distributed load? It's minus because the triangular load is downward. And remember that my moment function, the magnitude in the moment function for a triangular distributed load is m over 6, right? Where m is equal to, right, m over 6. So m is just equal to the intensity of the load, which is 120, right? All over the width of the load, which is 8. Okay, so that's m. 120 all over the width, which is 8. Right, of the distributed load, divided by 6. So it's m over 6. Okay? Multiplied to x minus 0. That's 0 because it starts at x equals 0. And I have a triangular load, so that's raised to 3. Next step is to perform double integration method. Okay? So my first step will give me the slope. Okay? That's equation A. Do not forget the constant of integration. Then I integrate further. This is now equation B, which is the deflection or the equation of my elastic curve. Do not forget the second constant of integration, C2. After I perform my double integration, my next task is to apply my boundary conditions in order for me to solve C1 and C2, and in order for me, right, to obtain my third equation, my next equation, which is a compatibility equation for us to solve the support reactions. Okay. Now again, I have here a prop cantilever beam, okay, meaning I have here a fixed support at A and a roller support at B. Therefore, I have 3 boundary conditions. 2 from my fixed support and 1 from my vertical reaction or my roller reaction at B. Okay? So now I just apply for my fixed support. I know that the slope should be equal. Okay? The slope should be equal to 0. So dy over dx is equal to 0 where, okay, at the fixed support at x equal to 0. Therefore, what I'll do is I'll just copy equation A because I'm dealing with slope, okay, dy over dx. Okay, so equation A is dy over dx. I'll just copy equation A and equate it to 0. However, I'll substitute the value of 0 to the variable x. Okay? So I'll just substitute 0 to the variable x, and notice that 0 minus 0, it's 0. 0 minus 0, that's still 0. 0 minus 6 is a negative answer, therefore that's 0. And 0 minus 0, that is 0. Therefore, it tells us that C1 is equal to 0. Okay? What's my next boundary condition? My next boundary condition is still at the fixed support. So aside from the slope being equal to 0, right, the deflection is also equal to 0 at x equal to 0. Therefore, I can use equation B at this point. Equation B, because I'm dealing with deflection, I'll just copy equation B. So this is equation B. However, what I will do is I'll just substitute the value of 0 to x, okay, in equation B. Therefore, this is 0, 0, 0, 0, 0, and evaluate. 0 minus 0, that's 0. 0 minus 0, that's still 0. 0 minus 6 is a negative answer, therefore that's 0. 0 minus 0, that's 0. 0 times 0, it's also 0. Therefore, C2 is equal to 0. Okay? And finally, my third boundary condition is that at the roller, I can say that if I have a roller, I can say that the deflection is also 0, but where? Okay, going back to the figure, let's look at the figure. Okay, y is equal to 0 at B, or at x equal to 6. Very good. Okay, so at x equals 6. Therefore, okay, using equation B still, y equation B, I can use equation B because, okay, I am dealing with deflection. Okay, so what I'll do is I'll just copy equation B over here. Okay? However, I will substitute the value of 6 to the variable x. So this is 6, 6, 6, 6, 6, and evaluate. 6 minus 0, that's positive, so I need to evaluate. 6 minus 0, evaluate. 6 minus 6, that's 0, so cancel. Okay? 0 times 6, that's just 0, and that's also 0. Therefore, my final answer here, once I evaluate, well, I won't have any numerical answer yet because I have two unknowns in this single equation, MA and R sub A. Therefore, I can rewrite this equation as 0 is equal to MA over 2, 6 squared, plus RA over 6, 6 cubed, plus RB, oops, there's already no RB since that's 0, minus, okay, 0.625 all over 5 times 6 raised to 5. This is now equation number 3. Okay? Now remember, I have two equations from my equilibrium equation, and this is the third. Okay? This is the third equation, my compatibility equation. Therefore, I now have 3 equations and 3 unknowns. Solving equations 1, 2, and 3 simultaneously, I should get RA, RB, and M sub A. Okay? Kindly double check if coming from equations 1 and 2, equilibrium, and equation 3, which is my compatibility equation, you should get the following answers for my support reactions. Okay? RA, RB, and M sub A. Take note that M sub A is negative, therefore, my initial assumption is wrong. It should be 79 kilonewton meters counterclockwise. Okay? Therefore, after which, we can now solve for the second problem, right? The second question, which is the deflection at the free end. So we are being asked to solve for the deflection at the free end, and I can use equation B, okay, in order for me to solve for the deflection. Okay? However, I can already solve, I can already substitute the values for MA and RA and X, which is, so Y, what is Y? At X is equal to 8. Okay? It's X is equal to 8 because that is the location of the free end which is being asked in the problem. So I'll just copy equation B, right? But substitute the necessary values. Right? Take note that M sub A is negative 79. Okay? Since I got a wrong answer, an opposite assumption, opposite of my assumption. R sub A is 66.5. Okay? And similarly, R sub B is 413.5 from our calculations over here. And my variable X, I'll just substitute the value of 8 to X. So I'll copy 8. This is 8. This is also 8 over here. This is 8. And this is also 8. So notice that in this case, I can already cancel this one, right? 8 minus 0, okay, so everything is now positive. So I can evaluate and say that this is, kindly compute, and show that this is negative 398 over EI, okay? And this is kilonewton meter cube, since this is deflection, and I haven't converted anything. So this is now negative 398 kilonewton meter cube divided by EI from the problem. Kindly remember that EI is 200,000 kilonewton meter squared. So I get negative 1.99 times 10 to the negative 3 meters. Therefore, to convert that to millimeters, I just multiply by 1,000. And that's negative. Therefore, it's 1.99 millimeters downward. This is now our final answer. Are there any questions? Kindly double check if my computations, my numerical computations are correct. So that's our second problem that we have talked about for double integration method for statically indeterminate members. I have another example here using the area moment method. So please practice solving double integration method for statically indeterminate beams at home. I hope you have learned a lot for this lecture. Right? So that ends our beam deflection lecture series for the double integration method. If you have problems, please do contact me through my email, or you can reach me through, send me a private message. Please do not forget to go back and review our previous videos. Okay? And don't forget to subscribe in order for you to be updated to our lessons and to our lecture videos. Until next time, thank you very much.